Greetings, class, and welcome to the next installment of our discussion of section 4.9 on solving systems of linear equations, linear differential equations. Here we're going to take a look at exercise number 2 from section 4.9. It features these two equations that you see right here. First of all, dx dt equals to 4x plus 7y. And then the second equation, dy dt equals x minus 2y. So here we have two relationships, two differential equations involving functions x and y that are both functions of the independent variable t. And our goal is to figure out what those functions x and y must be to make both of these first order differential equations true. Now, as we go to solve this, it's useful to rewrite both of these differential equations using the differential operators that we introduced in the first video. So the first equation, dx dt equals 4x plus 7y, is of course the same thing as dx dt minus 4x minus 7y equal to 0. And we notice there, as we're taking a look at that equation, that two of the terms there, the first two terms, both involve the function x. Dx dt is the derivative of x, and then we have minus 4x. What we're going to do is we're going to take those two terms and we're going to write them using differential operator notation. With differential operator notation, that would be written as d minus 4 of x. That indicates that we're taking the derivative of x, which we are, and subtracting from that 4 times the function x. So that's the differential operator notation for our first equation. If we do likewise with the second equation, we're going to see that that can ultimately be written as d plus 2 of y minus x equals 0. So there we have our two equations there. And what we're going to do now with that is proceed further onward here. Let me erase my marks there. All right. So now we've got these two equations in differential operator form. And what we want to do is we want to eliminate one of the functions from the differential equations. In the first equation, we see that we have negative 7 times y. And in the second equation, we have d plus 2 of y. Now, if we wanted to eliminate the y function entirely, what we could do is we could apply the differential operator d plus 2 to the first equation, because that's the operator that appears in front of y in the second equation, and we could multiply the second equation through by 7. If we do that, if we apply the differential operator d plus 2 to the first equation, which essentially means we're differentiating and doubling, doing those two operations to the equation, we'd end up with d plus 2, derivative with respect to t plus 2, of d minus 4, derivative with respect to t minus 4 of x, minus 7 times the derivative plus 2 times y equals 0. So there we've applied that differential operator to both sides of the equation. Obviously, if you take the derivative of 0 and add 2 times 0, you still get 0 on the right-hand side. But we've now applied that differential operator d plus 2 to both sides of the first equation. I'm going to take the second equation and multiply through by 7, just taking 7 times every piece. So 7 times derivative plus 2 of y minus 7 times x equals 0 times 7, which is again 0. So now we've got these two doctored up equations. After applying the derivative plus 2, in other words, differentiating plus doubling to the first equation and multiplying the second equation through by 7, notice right now that we've rigged things up so that what's being applied to the y function, which is minus 7 times derivative plus twice, is exactly the opposite of what's happening to the y function in the second piece. That's positive 7 times the result of differentiating and adding twice the function. Because those are equal and opposite, if I add those two together, those pieces involving y and its derivatives will vanish. And what will I be left with? Well, on the left-hand side, I'll have derivative plus 2 of derivative minus 4 of x minus 7 times x equals 0, because on the right-hand side, 0 plus 0 would give me 0. So now what I've got is a left-hand side that really says, well, if I take a derivative of a derivative, that means I've taken a second derivative. If I take 2 times the function that was the first derivative and minus 4 times the function that was the first derivative, I have minus 2 times the first derivative. And if I take 2 times negative 4 times a function, I'll have negative 8 times a function. But negative 8 times a function minus 7 times that function would be minus 15 times that function. So in other words, we have a new differential operator on the left-hand side. Second derivative of x minus twice the derivative of x minus 15 times x equals 0. And I've rewritten that here in its typical non-differential operator form. Now that's a second-order linear homogeneous differential equation with constant coefficients. And its auxiliary equation, which is m squared minus 2m minus 15, notice the similarity between the auxiliary equation and the differential operator. That auxiliary equation has roots of m equal to positive 5 and m equal to negative 3. So that means that the solution for this homogeneous differential equation, which is our function x, is c1 times e to the 5t plus c2 times e to the minus 3t, using our theory from early in chapter number 4. And voila, we are now halfway done. We have found the function x that makes both of the original two differential equations true. Now, by analogy to our usual techniques for solving systems, once we find one of the things, which here is one of the functions, we usually do a back substitution to one of the original equations to find the other one. Now, we will remember that one of my two original equations, this is the first one of the two, said that the derivative of x with respect to t equaled 4 times x plus 7y. Well, that equation can be solved for the function y. If we subtract 4x from both sides and divide by 7, we're going to see that y is 1/7 of the difference between dx dt and 4x. But we know what x is now, and therefore we also know what the derivative of x is. The derivative of x is going to be 5 times c1 times e to the 5t minus 3 times c2 times e to the minus 3t. And if I substitute in that expression for dx dt and the expression for x into my formula, I see that I've got 1/7 of 5c1 e to the 5t minus 3c2 e to the 3t minus 3t minus 4c1 e to the 5t minus 4c2 e to the minus 3t. And I can do some algebra. I can combine the terms involving e to the 5t and the terms involving e to the minus 3t. And when all is said and done, after the algebra, I'll have that y of t equals 1/7 of c1 e to the 5t minus c2 times e to the minus 3t. Now notice those C1 and C2 are the same C1 and C2 that appeared in the expression for x of t. In other words, once we pick the C1 and the C2 for the x function, that essentially determines what the coefficients have to be for the y function. There aren't four unknown constants in x and y. There's only really two. Once we specify the C1 and the C2 for the first solution function, that's going to essentially determine what the coefficients are for the second function y. All right, so there you have it. Another example of solving a system of two differential equations with two unknown functions of the variable t. I hope this has been again instructive to you and wish you well as you work towards mastering the material from this section.